Hey guys, it's Chili here. Welcome back to 3D Fundamentals tutorial 19. Today we are going to take our 3-component vectors and our 3x3 matrices, and we are going to convert them to 4-component vectors and 4x4 matrices. Now you should already be familiar with this process because we've covered it in advanced, I think it was episode 5, where we were working with 2 dimensions and we had 2x2 matrices, and we converted over to using 3x3 matrices. Now the reasons for doing this there's a few reasons. First of all, it allows you to represent your translations within your transformation matrices instead of having to add a separate vector after you multiply by the transformation. And also, it is going to, in 3-dimensional graphics, it's going to enable us to create a projection matrix, which will do a bunch of stuff for us, but that's going to be in the next video. I was actually going to put this stuff together with the next video because it's a pretty light topic, but since the next video is a little complicated, I decided to get the 4x4 matrix stuff out of the way first, and then we'll look at projection on its own. So, let's get started. So you can see here in the commit details, I've deleted mate2 and mate3, and I've just created a header file called mate.h. And the reason for this is because for matrices, it's actually better to just template the size itself. So now I have one class that represents any size of matrix I want. 2 template parameters, the type and the dimensions. And in doing this, life is pretty good. Now I can just have type def or using, for mate3, mad3, mate4, mad4. It's all in one implementation here. It's all parameterized. Most of the stuff actually doesn't change. I mean, this doesn't change, this doesn't change, this didn't change, this didn't change, this did change. The matrix by matrix multiplication. Before here, for the loops, I just hard-coded the dimensions of the matrix in here. So for mate3, this would have been a 3, and for mate2, this would have been a 2. Now I just put the s in here because s is the matrix, or s is the template parameter that gives us the dimensions of the matrix. But other than that, it's all the same. And the other change here is that now, for our static factory functions that generate our basic utility matrices like scaling and rotation, now it's going to have to give us a different matrix depending on the dimensions. So what I've done for this is I've used if const expression. So the const expression if will actually, at runtime, there will be no conditional here. This is actually a compile time conditional, so depending on what s is, whether s is 3 or 4, it will compile this code or this code. So it's a little bit of an optimization. It's just I think it's a good usage of if const expression here. I don't have the syntax correct here. It'll be corrected in a later commit, but this is the general idea. So for identity matrix, this would be for 3x3, this would be for 4x4. We could have done this parameterized, but for some other matrices, for 3x3 and 4x4, it's not quite as simple. Here, it's not just an extension of the 3x3 case. It's actually got a different thing in here for 4x4. So, the basic idea is for your matrices here, 3x3 and 4x4 are going to be the same, except in the 4x4 case, at the diagonal here, you're going to put a 1, and that's just to maintain the 1 that is going to be, in the W position. So, I guess I could go over a quick little refresher here. So in your standard 3-dimensional vector, you've got x, y, z, right? Now, when you make that as a 4-component vector, you're going to add another component that we call W. And W is usually just going to be 1. And the reason for that is this here is a translation matrix. Should be somewhat familiar to you if you have watched Advanced 5. And the translation matrix, the translation amounts are held in these components here. So when you multiply this vector by this, you're going to multiply, this column by this row, and that will give you your Let me put this here. That'll give you your x value right here. So when you multiply this, you're going to get x times 1, which is x, plus y times 0, plus z times 0, plus w, which is 1, times translation x. So the thing you end up with is x plus the translation value, which is what you want for a translation matrix. So this 1 here, its primarily job in this case is to activate this translation value so that it can be added to the x component. So this is the setup that we have, and that is why this w component is generally set to 1. And for your other matrices, you're going to want to keep this 1 in here so that when you multiply x, y, z, and w, you're going to end up with just a 1 here. If you started with a 1 here, you're going to keep that 1. You want to maintain that. It's very important. So that's why you see in all these matrices here, this element is always set to 1 to maintain w equal to 1, or to maintain w at its current value. So yeah, we have all these matrix generators here for 3-dimensional and 4-dimensional case. And down here, maybe translation. So here's our translation matrix. It's what I showed you before, x, y, z. There's actually a problem here, but I will get into that in just a little bit. And then down here we have multiplication, and I didn't add the case for multiplying a vec4 times a mate4 because I haven't gotten that far yet. This is only just creating the general matrix template class. So that's that. Let's look at the next commit. So in this commit here, I implement vec4 and I do a small mate4 translation fix. So let's look at the fix here. So I've moved the translation values from this column here into this row here because that's where they should be for our current system. And I've also, you can see here, added functions for multiplying a vec4 by a mate4. So it's the same idea as vec3, only you've got, more elements here. So why do we need, why is it got to be in this row and not in this column here? Well, the thing about this is what I'm using in the system that I've gone with here, the notation, and then sometimes it's confusing because I write it out as a column vector, right? I often write x, y, z, w, mainly because that's what I'm used to. But in actuality, the notation that Direct3D uses, and by extension my system here uses, is actually, conceptually, it's a row matrix. So it's x, y, z, w. And in that case, remember, w is going to be 1 in general. So you're going to multiply this row by each of the columns, and you're going to add that result to get your rows in here. So to get your x, you're going to multiply x times 1 plus 0 times y plus 0 times z plus 1 times tx. So as you can see, you've got to put your tx, your ty, and your tz down here, not here, because we are using a row matrix notation, not a column matrix. In general, it doesn't really matter what notation you use. So now let's take a look at what I did in vec4. So it's a new function, not a new function, new class here. Same idea with the type defs. Basically, I just copy and pasted vec3, and then I replaced a whole bunch of stuff. I added w in here. You might notice something weird. Just pay no heed for right now. But here's the thing. A lot of these member functions or operators or whatever, we're not going to use them for vec4 because they don't really make sense. Things like length. It doesn't make sense to take a length of a vec4 because usually in 3-dimensional space, you're only interested in the x, y, z part. But since w is always going to be equal to 1, that is going to add, it's going to screw up your length. And so we generally only want to take the length of the x, y, z part. So we don't need the length of a 4 dimensional vector, so I didn't add it. I didn't add length stuff. I didn't add normalization because that's related to length. I also didn't add dot product because we don't really take the dot product between two 4-dimensional vectors. And cross product, don't usually do that either. I don't even know if it's possible. I don't think it is. But the other stuff, yeah, I mean, saturate, sure, because we use that for colors, right? And we have RGB and also A. So we might want to do 4-dimensional saturate. Hadamard is also a color thing, so I've added that in there. But a lot of these functions, they don't make sense for 4D vectors, so we don't put them in. You might be asking, well, then what if you want to do your 3-dimensional, you want to get the 3-dimensional length of a 4-dimensional or 4-component vector? The answer is, well, because this inherits from a vec3, I could just cast it to vec3 and then call the function on the casting part. So I could cast it to a reference to vec3, call the function on that, and it would work fine. We might do that later on, but for now, this should be fine. We do, however, want the basic operations of addition, subtraction, multiplication, and division because we need that to do interpolation. For our vector to be able to run through our pipeline and be interpolated correctly, it needs to implement these basic operators. And we do want to interpolate a 4D vector, both for colors and for space. So we have to implement those, but we did it. And also in here for vec2 and vec3, I just did a little fixing up here. I realized I don't really need this. This could just be equals default, so fix that. And there you go. What did I do down here? Yeah. So I little bit of a boo-boo here that I never really realized and never became a problem, but probably should fix that when you notice it. Let's move on to the next commit. So in this commit, I fix some derpage. Let's look at the derpage. Well, first off, I want to add a constructor that allows me to construct a vec4 from a vec3. So I can pass it a vec3, it'll create a vec4 with w equal to 1, or I can pass it a different w, and it will give me a vec4 with the vec3 plus the w that I've chosen. So it works both ways, nice and convenient. Derpage is obviously, we don't want to be assigning to z twice, we want to be assigning to w. This will cause us problems down the road. And here, forgot to add the w, so we add that in there. Just a little bit of bug fixage here. And finally, one more fix to mate 4. My syntax for const express if wasn't correct. You have to put the const express in the else if as well. Apparently, I'm really not sure about this one. I haven't used const express if a lot, so this was my first experience, and the CPP reference page was, in my opinion, a little misleading. So in my defense, here's the page for const express if, and it says here, if const expr this, else this. It doesn't have else const expr. So I was like, well, and here it says if const expr, else if, else. Now, this did not compile for me. I put it in the compiler, and the compiler said, this is some bullshit. So I had to put a const expr here to get it to compile. So I don't know what's going on. Maybe, I don't think that CPP reference is writing bad stuff. There's maybe something I don't quite grasp here. But either way, it's not super clear. So, anyways, no word to the wise. You gotta, when you're using it like this, at least you gotta put a const expr after this else if. It seems to work fine when you don't put it here, but I don't know. Maybe if I tried to put s equals to 5, the compiler would get mad at me or something. I don't know. Who cares? This works, so this is what I'm using. A little bit of a fix. A little bit of a syntax fix, nothing major. And here we actually transform one of the effects to use 4-dimensional vectors instead of 3-dimensional. Now, the beauty of this system here, the beauty is that vec4 inherits from vec3. And in doing so, we don't actually have to change anything in the pipeline itself. The pipeline can actually stay exactly the same, and it still runs fine. So all we got to do is we go into the effect, and what we're doing here, we don't even have to change the input vertex type. We can take the same kind of input vertex. We can use the same generator function that I think for our case we're loading from a object file. Use the same function that spits out vec3 for position and normal, And then all we do is for the output from the vertex shader, we're going to output vec4 for position and normal instead of vec3. And we can actually leave the world position itself as a vec3. Now you might be wondering, well, why can this one be a vec4, this one vec3? Why can this one be a vec3 when you want this one to be a vec4? Is a better way to phrase that. And the reason why I'm doing it this way is the position itself. This is the position that's going to be used to determine the pixel on the screen. This is going to, in the future, be going through the projection transform, and the projection transform is going to want a vec4 because it's going to have a 4x4 projection matrix, whereas vec3 for the world position, this is only going to be used by the pixel shader. It doesn't really need that. It's not going to go through the projection transform, so it doesn't need to be 4x4. So we can leave that as a 3x3. And a few things change here. Let's look first at just the actual shader function itself. So in the old one, we multiply the position by the rotation, we add the translation, and then we multiply the normal by the rotation, but we don't add the translation because you don't want to translate your normals. You're going to stretch them. They will no longer be normals anymore, and they will also no longer be pointing in the same direction that they were before. So in the new system, all we're going to do, if I can freaking scroll this over, is we are going to multiply. We're going to convert the vec3 to a vec4, and then we're going to multiply that by the transformation matrix, which includes rotation, scaling, and translation all in one shot. You do that. And then we're also going to create a vec4 from our normal, but we're going to set w equal to 0 and multiply that by our transformation. Now you might be saying, well, Chili, if you multiply by your transformation that contains a translation, you're going to be translating your normal. That's really bad. But notice, we're setting w to 0 here. So if w is 0, when we multiply this out, what are we going to get? We're going to get x times 1 plus y times 0 plus z times 0 plus translation x times 0. So we're just going to get x, which means the translation was not applied. So by setting w to 0, you can have vectors that are immune to translation, and that's really big. So vectors that are immune to translation, we just call them pure directional vectors. And it's a beautiful thing to have, because now you can use the same transformation matrix for your point vectors in space as you use for your directional vectors, and it will work accordingly. It's another beautiful little side bonus of using 4x4 vectors for your translations, your transformations, I should say, which include translations. Always gets me. But anyways, so that's why we set this to 0. And we do that, and it's all good. Now, obviously, for our vertex shader, we don't have to store separate rotation and translation. That's all included in a single mate for the transformation. And so now we don't need two functions to bind rotation and translation. We just have a single function that binds the whole transformation. That's just going to set that there. And that is all you have to change, really, in here. Nothing else changes. It's quite beautiful. And that's, again, a side effect of that we inherited vec4 from vec3. Made our life a little easier in this case. Now, if we look, we also have to do a little change for the scene, because now there's no more bind rotation and bind translation. Now we just bind the transformation. I might have misspoken before, but let's just roll with it. So we bind transformation, we concatenate x, y, and z with a translation matrix, and then we're done. That's all. That's the only change that needs to be had. And I can run this, but it's not going to be incredibly interesting because nothing actually changes in the scene itself. The only thing that we've changed is how things are done behind the scene. So you can see here, it's our same model, same effect. Nothing's broken. Everything's the same, but under the hood now, we're using 4x4 matrices to do the transformation, and we're using 4-component vector. And that's it. That's all there is to introducing 4-component vectors into our system, 4x4 matrices. And again, like I said, it might seem a little weird to have this extra component W that is almost always 1 and sometimes 0. It seems like a bit of a waste, but it's going to get a little more usage in the next video when I talk about the projection matrix. There we see W has a little bit of a bigger role to play. But until then, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more 3D fundamentals.